Okay, so good morning, everyone. Let us begin. Before I hand it over to Luca, I just have a quick announcement to make for the exercises. The first exercise that you need to do for the grade bonus is live on Moodle, so if you want to work on that, you have around 2 weeks. A note on that, if you're using Windows with Windows subsystem for Linux, it won't work right now. We aren't sure why. It doesn't seem to be a problem with our code, it's a problem with WebGPU. So if someone has made it work, tell us how you made it work. But we can't do much about that, and you can still use Visual Studio, so that should work. And a note for Windows users, if you try and run the code, make sure your path has no spaces in it, because that will also break it. So that's all I have to do. So any questions on the exercises before I hand it over? Doesn't seem to be the case, so enjoy Luca's lecture.
Okay, good morning, everyone. Welcome back, and today we're gonna talk again about mass spring systems. Before we go on, and first off, was there any question that came up by looking at the slides from last time that maybe you wanted to ask before we start? No, so that's good. So first off, we're gonna go through a quick review of the notation that we have. So last time what we were trying to do was to integrate numerically ordinary differential equation, and in this setting we have y, which represents the target function that we want to compute. X in this case will play the role of a free variable because we are using a sort of notation that is typical for mathematics rather than physics, and so in this case, for instance, the target function can be your trajectory that we want to compute for each individual points, and then the free variable will be time. Now, with y prime, we are defining the derivative with respect to x, that in our case would be the velocity. And one should take into account the fact that y is only dependent only on one free variable, so we can derive it only with respect to that variable. Otherwise, we would have, if we have a dependency, for instance, in space and time, then we would have a partial differential equation because we have different derivatives with respect to different free variables. Now, when we are computing the solution, we are not really able to compute it analytically most of the time. So what we try to do is that we discretize both the free variable and the target function. And normally, when we are discussing the discretization of the free variable, we are usually discretizing with a constant step size, which we define as h in this setting. Finally, we are going to proceed integrating the equation step by step in an autoregressive sense. So what we are going to do is that we are approximating the function over and over again, and since we cannot access the actual value of the function at each and every step, but we only know its approximation, we're gonna see that again in a moment, we are gonna indicate with y subscript n the nth approximation or nth step of the approximation of our function y. So the basic thing that we are going to use for our work is based on Taylor expansion. Taylor expansion is a very useful mathematical tool that allow us to approximate the function in a given point based on the derivatives calculated in the very same point. Now, as we said before, we are going to discretize the free variable, and in this case we're gonna use these notations. So the nth step, or n in the free variable, by is gonna represent it like that, and whenever we are adding our discrete step size, we're gonna get n plus 1. Now, we can perform an expansion of the value of our target function y at position x n plus 1 in an exact way by using Taylor expansion. Taylor expansion is written in this form, and in the general, let's say, general expression for that, this is actually a sum, an infinite sum, so in which we are computing the e derivative dividing by the I dot and power of I. So this representation is exact only when we are considering all the elements in this sum. So we have an infinite amount of terms that we need to sum. Of course, this is not very practical, but it's a useful tool that allow us to calculate and define how far we are approximating a certain function, because we are typically using just a limited number of terms in this summation. So for this, we need to probably truncate the approximation to a certain extent. So in general, we can write our approximation in this form, and here this term is what we use to indicate the error that we are performing, and typically gives us an error that is proportional to a certain power of our discretization step size. So one important thing that we see here is that what we have, since we are able to calculate all these terms in an analytic way, because we assume that we know a certain order of the derivative and we calculate its value, then what we have here is a polynomial, which is a function of the steps of the discrete step size, which is h. And so in this case, for instance, we are using a second order polynomial in h, and given a starting point, what we do is that we advance our free variable by a given step. And it's important to notice that this value is not approximated, because you are just making a summation. So we have x0, and then we add h, and we know exactly what is the value of the free variable. What we don't know is the value of y of x, which is the function that we want to approximate in practice. So here what we use is an approximation based on this polynomial that we see right here and the derivatives that we calculated in the position x0. And we proceed approximating the value of this function step by step over and over in time. And as you can see, the error that we are making is not necessarily positive or negative one, but is typically in the order of this term that we have at the end, and we see a more precise, let's say, estimate of this error later today. So coming back again, we have this formulation, and the simplest, of course, it doesn't, let's say we can make a constant approximation, so if we are considering only the first step, but of course trying to approximate a function that varies with the free variable with a constant, one can use this approximation, but in general would be relatively wrong. So the bare minimum that we can do is that we can consider the linear term, which is the one proportional to h. And this is something that we have already seen, which is in practice Euler's method. In fact, now what we do is that we are using this method that was developed a long time ago. And what we do is that we take the initial value, so where we start, and then our approximation, and first order approximation, is just given by taking the tangent of the function at that point, and then assuming that our solution is moving linearly. So what we obtain, let's consider a function that is written like this. So we have an expression that is analytical for the first derivative of this function and depends in principle both on the free variable and on the function itself. And we consider initial conditions for the free and dependent variable with a given step size. And now our step is gonna be something like this. And as you can see, if we substitute these y prime in this formulation, because these are the same, then you can immediately recognize that what we are doing is in practice the first order truncated expansion, Taylor expansion that we have seen in the previous slide. Now, there will be a lot of y's, a lot of x's here, so it's important that we get the notation straight. So first off, here we are writing y subscript 1 when we are defining the approximation of y starting from the point for the function evaluated in x0 plus h, which is, by the way, x1. And once we have computed y1, we can proceed and compute f of xy y1, x1 y1, and proceed so on and so forth to our desired time. Now, it is very, very important to remind that yn, so our nth approximation, does not equal the in general the solution at a given time step, because we don't have really access to this solution. That's what the actual function that we are trying to approximate. So in general, also, it's not easy to write an error with respect to this or an exact error, because we don't know the function that we want to approximate, so we cannot write an error, so a difference between these two terms. So what we usually do is just to write an estimate of this error. Now, yeah, so this is a notation that we use just for the approximation, and it's important to keep it in mind, and while the other one is the actual function. Right, so let's have a look at a more visual, let's say, example. So now in this case, we have a plot here. Now the free variable x, that can be, for instance, again, time, and now this is supposed to be the trajectory. And what we want to approximate here is this thicker black curve, which is our trajectory, so how y evolves with respect to x. Now, in order to start our integration using Euler method, what we do is that we start with the free variable x0, and we are able to calculate the first value of the target function at this point that we will call y0. Now, once we have this point, we can calculate the tangent there, and we use this information to proceed and move over time. So, right, so the next step here is gonna compute the free variable here. As we said before, this is exact, so it's just summing up this value. And then, by using this definition, we can find y1. And y1 is defined with in first approximation with this expression that we have seen before through Euler method. And you can definitely notice here that the orange point is not really, let's say, is not the same as the black point over the curve. But remember that normally and in principle, we do not have access to this black curve, especially also if you think about these in higher dimension, then we are not really able to know the difference beforehand. In this case, it's trivial because we have an example, but in general, this is not possible. And this value that we have here, y of x1, is definitely not the same as this one, which is what I was warranting before. So just remember that we don't know the function, the actual function, and that's really important. I'm stressing it a lot, I know, but just make sure that it's something that you know. So, okay, like repetita juvent, but this is a bit too much. Now, what is happening here is that once we got our first point and our approximation here, then what we can do is that we can advance in time to another point. So we compute again the free variable on another step. We estimate the tangent not here, but here. And using this information, we find our next point. and so on and so forth. So we proceed using this information. And as you can obviously tell, the more step we perform, the more it's possible that we deviate from the original trajectory, because there is always an error with respect to the first point that we are going to estimate. So, in summary, what we have is that we perform an update at any time step based on the previous time step, and it is important here to point out that let's say this is always we perform this in an autoregressive way. So based on the previous solution, only on one point in the previous solution we we calculate the next. The other important thing is that you see only values, and the first point, the previous point regarding the fact that we are using one single point is important, because of course we could potentially use more information, and that's gonna be the topic of multi-step methods that we see in a moment. And the other remark that I want to make here is also that we are using only the value of yn. Yn is a value of the function that we know, because we have already calculated the value at this moment, or our approximation of it at least, and then we calculate the next one based on that. There are other methods that, let's say, consider on the right hand side of the equation also yn plus 1, but those are what we call implicit methods, and we're gonna have a look at them also later in this lecture. So what we do is that we approximate the slope by using the tangent in the current solution, and then we take a step in the direction of the estimated tangent. Now, what does this method gives us? What does it gives is a first order method, which means that our approximation is, as you saw in the previous slide, we were diverging relatively fast from the previous value, and this is even, let's say, more important whenever the function has a variation of the tangent that is especially quick. So for instance, if I have a function that goes like this, and I estimate my tangent here, then my approximation will give me a solution that is higher up, while the function in that point is going down. And based on this information that I have written here, I have no idea and no possibility to know that this function will actually drop sharply like it does in here, and then this will give us eventually a very large error in the computation. So we would really like to have something better than that. But before going there, one, let's say, common question that we get when teaching this course is, for instance, why don't we just integrate the equations directly? Which is a fair question. And one important thing here is to say that in general, if we are dealing with a single particle, with a single object, as we were seeing in the last lecture, then this is not particularly problematic, and we can actually integrate with a reasonable effort the equation. But as soon as the expression for the derivative, which is f, is given by a much more complicated expression, a much more involved calculation, then this becomes quickly very difficult and very very troublesome to perform. In general, on top of that, there are also functions that we literally cannot integrate. So for instance, if your derivatives look like something like these, for instance, then there is no analytical way of integrating these using the typical tools that we use. Or for instance, I don't know, this one. This is supposed to be a 4. This function, again, does not have an integral, even though it's, well, it does have an integral, in fact, but it's not an analytical one. So we always need to, let's say, resort to some numerical methods, even in extremely simple function like the one that we have here. right? So it is important in general to proceed numerically in this situation. So the next question is, how can we do these computation in a better way? Now, we've seen a first order method, and the next one, which is known as IN method, is a second order one. And the idea behind this method is that instead of taking, of course, we have seen that taking the tangent at a given point is an extremely rough approximation of how the function will behave. So the next attempt is, okay, let's try to have a better informed or a better estimation of the tangent that we get. So, or well, the tangent estimation is correct. A better estimation of how the function will evolve over time, and to perform the prediction of the next step. So this estimation is based on the current state and also on an additional Euler step that we are going to perform. So the method looks more or less like this. We take our Euler step here, and in this case we start as usual by, in our point, x0, y0, which is our standard start point. Then we compute an estimate of the solution y tilde at a given time step, at one time step further in time. Then what we do essentially is that we perform a second Euler step. However, what we are doing is that we are still performing a full step, but we are averaging the value of the tangent that we get at the initial point with the value of the tangent that we get in a point slightly farther away. So you should, one good way to see this is probably like looking at this like that. So this is the averaging operation, because of course we are having the sum of two different terms, and we are always doing a step that is of the same size, which is the size of h. And by doing this simple trick, we get actually a second order accuracy. Now, it is important to mention here that let's say this second order accuracy doesn't come like for free, but of course we need to perform two different evaluations of the same function, because of course in order to step only at y1 we need to compute both this value, which was the one that we were computing when we were using Euler step, and at the same time we also need to use to evaluate a second time this function. In general, from, let's say, a mathematical point of view, of course this is an additional a third evaluation of the function, but of course if we are smart enough, we can, when we are programming this, we can just save this value and then we store it somewhere. Of course this requires some more memory, but in general that's either a scalar or a matrix of the size of our system, and we can definitely compute, we don't need to recompute this value, evaluate this function that can be arbitrarily costly. We don't really know how much it is expensive, so let's keep it on the safe side, so to speak. Once we do all these, by only doing two evaluations, what we get is a second order method, and we can have a quick visualization of this method here. So what we do is that we still have our x0 free variable and x1, which is the free variable at the next time, as we have already seen several times in the last steps. We perform our first estimation, which is y tilde, and then now, as you can see, the approximation is fairly rough, and what we do is that then we use this information to compute the slope also in that point, and by averaging the value of the orange slope and of the green slope, so the slope at y0 and the slope at y tilde, what we get is that we have a better estimation of the value, and as let's say in this case it's fairly even visually easy to recognize that our estimation, the blue one now, it's much better estimation than the one that we got before. And we're gonna get into, let's say, quantifying how better this is just in a moment. And one interesting thing of this approach is that essentially what we have is what we would call a predictor corrector method. So the first step represent the prediction of the slope. So we get a first approximation of the slope, and then by computing the second derivative, the second time the derivative, and averaging that value, we try to correct our estimate, our first prediction, in order to step forward and have a better educated guess of what the function will look like at the next time step. These is, of course, as we said, is we have twice the computational cost, but in general, this is not the only way that we can achieve a second order method. Another straightforward way of integrating is using midpoint method. And what we do in this case is that we evaluate the derivative at an intermediate half step. So before, if you remember, what we were doing was averaging the value of the function at two evaluation which were distant one full step. In this case, we take an intermediate half step that gives us, again, second order. Okay, so in this case, the equation look like this. So you can see that now our step is half of the actual value that we are taking, and we can have y tilde that in this case is not a full step but just reaching up to the middle point, and then so an intermediate step, so to speak, and then we use the knowledge of the function in this intermediate step. And it is important here that we use also the corresponding free variable, because if we are taking half a step in the prediction step, then we want to evaluate the function also in the free variable with alpha step. So this is something that it is important to remember, because might be overlooked, because let's say we write just the value of x1 and this is going to give us a wrong estimation of the derivative, and that's not second order for sure. And in this way we are able to achieve second order like in the OIN method. Now this second approach is is better known as Runge-Kutta second order. Now, what are Runge-Kutta methods? Runge-Kutta methods is essentially is a family of integration methods that were developed by these two mathematicians, and they can provide us essentially an approximation of our function up to an arbitrary order by providing a certain formula of all the intermediate steps that we need to perform. In particular, we are gonna have a look at Runge-Kutta fourth order, which is usually shortened to RK4. And what we do here is that we perform 4 different steps. So first off, we compute an estimate of the slope, and we're gonna keep track of this value by using this k plus a certain subscript in our notation, and then by using this information we predict the tangent at the midpoint. Once we know that value, we try to provide a corrected estimate based on this value, and all the time we are, let's say, recording and keeping track of the value of k1, k2, k3, and finally we make a prediction of the slope for the full step using all the time, maybe I didn't show it here, but at every step we are using the information that we have obtained at the previous step in order to get a better and better approximation of this value. So we do the fourth step, and then finally what we do is that we perform the actual step, just putting together all the updates that we have obtained over time, and this approach will lead us to a fourth order method, which is, let's say, much higher accuracy than what we have seen before. Now, let's try to visualize this in the same way that we have done before. So first off, K1 gives us the first estimate of the slope as usual. Then by using the estimated value in this point, we compute the tangent at that point, which is now our K2. We then proceed to correct these estimate in our third step and obtaining K3. And then finally we get K4 by performing a full step prediction, and we get let's say the approximated slope there, and then the final result is just putting everything together in this formulation that we find here. So in general, Runge-Kutta methods. Questions so far? Yes. Sorry. So you can think about this case to be like approximation of the slopes, different approximation of the slopes. And since we don't know the value of the function in those intermediate points, what we always use is just, the step using the latest approximation of the slope that we have. So now, sorry, I'm gonna go back to the slide for Runge-Kutta. So for instance here, in the second step, we don't have access to the value, the actual value. So we compute our placeholder for the y value is gonna be, let's say, the one that we have written in the slides before. So like we're gonna use y0 plus k1 plus the step essentially, and then we so on and so forth along all of the step. Right, so we got an estimation. Runge-Kutta is very nice. So one could ask, yes, you could ask. So how can we correct the slope if we don't know the function? As you can see from these steps, essentially, what we are doing is that we are correcting it by, let's say, making up our known knowledge of the system of the function by making several estimates of it. So what we do is that if I have one point and I have a slope there, then the function could go, let's say, let's draw an example. So if I have a function looks like this, and I get an estimate here, then I get that the estimate of the next point is here. But now, if I am computing the slope at this point, let's assume that the field is more like is the same, because the gradient field is everywhere, is not only along the trajectory, so we can always compute f, even if it's a wrong point, so to speak. By using this estimate, now I see that my derivative points down, which means that if I do the average of these two computation, then of course is gonna kind of lower down my estimate of where the next point lies. And essentially what we are doing is that we are performing more evaluation and more steps that gives us a better estimate of the tangent, even though we don't know the function. Let's say potentially if you were able to compute this function in every single point using an estimate, then you're gonna get a very good estimation of the function. While in this case, the more points you had, the more knowledge you are adding to your estimation. If it does make sense. If it does make sense. Good. Right. So now, Runge-Kutta. We can make integrators of any order, in principle. Now, the question is, why then choosing 4? Because it's apparently seems a very arbitrary value. The answer lies in this table. So this table shows us on the first row the order of the method that we are able to obtain, while the second row gives us the minimum number of steps that we need to perform in order to achieve such accuracy, and we are able to prove that such accuracy can be indeed obtained. So as you can see, as far as like 1, 2, 3, and 4, the number of steps grows at the same speed of the order that we are obtaining. So remember that the more evaluation we do, the more computational cost we need to put in this operation in order to do one step. So we are always doing a single step of a given size. So it is important here to balance the trade-off between how much the calculation is costing us in terms of computation and the accuracy that we are getting out of this calculation. And whereas, as you can see that as we move to order 5, 6, 7, and 8, then the number of steps that we need to perform is actually increasing faster. So from here, we are getting, let's say, lower return in terms of the by adding the computational cost of a single step. We are not having the same accuracy gain that we are getting from a Runge-Kutta method of the 4th order. So in that sense, Runge-Kutta of the 4th order represents to some extent a good trade-off between these two qualities of the computation. And in that sense, Runge-Kutta represents a relatively good compromise. Of course, we don't necessarily need to perform a 4th order evaluation of the function, and that could be helpful in general. But also for, let's say, calculations, we can always use also a 2nd order Runge-Kutta method, and that's gonna be absolutely fine in general. So let's have a brief recap of what is happening here. So we have Euler method, which was a first order accuracy and requires only one evaluation of the function. We then step to OIN method, or the midpoint method, that provides 2nd order accuracy with 2 evaluation of the function. And then finally we have Runge-Kutta, 4th order accuracy, although we need 4 evaluation steps. Oh, sorry, I'm just one line ahead of the presentation, looking at the wrong side. Okay, so now the question now comes in probably very immediately in your mind, is like, why don't we just perform 4 steps of Euler instead of using a 4th order method? Because why should I go through these lengths and try to perform a better estimation of my function, so on and so forth, just to obtain something that, if I reduce maybe the size of the step and do more steps, more smaller steps, possibly I'm getting a better estimation? Well, that's something that we're gonna have a look at. And what we do, I mean, I will not try to convince you only from the mathematical perspective, but also from a practical perspective, showing a little bit of an example. And what we do is that we have a look at this very simple function. So we consider a function whose derivative, 1st order derivative, is actually the function itself. Is there any function that comes to your mind that is exactly equal to itself once we perform a derivative? Yeah, exponential, exactly. So the exponential function is a solution of this calculation. And one nice thing of this example is that since we know the solution, we can compute exactly the error, because normally this is not possible for us because, of course, we don't know the exact solution. If we knew the exact solution, there was no point in doing all this. That would be unnecessary pain. Instead, in this case, though, it allows us to give us an estimate of how the results are computed. And and for instance, whenever in this case, it's actually also the calculation are very simple, because if we substitute the value of y prime in the Euler step, then what we have here is that we are just summing a scaled value of the current function. So this works in a sense like an accumulator of some sort, and that's relatively simple also to implement. And so the way we're gonna go about this is that we're gonna consider a certain interval that will go from 0 to a certain x, and we want to do this by using a specific number of steps. And in this case, what we do is that we compute the exact error based on the current solution using these approximations. So by modifying the value of n, we're gonna get an estimate of how fast our computation improves, our accuracy in the computation improves, and so this will give us, let's say, an intuition of how good or how bad our different methods perform in this case. So what we do is that we're gonna write a simple C++ code that is gonna do the integration of this function for us. We're gonna aim to obtain an error that is more or less floating point, single precision floating point accuracy. No, well, no, not really. But let's say 10 to the minus 6 is enough for our calculation, also because if we go below, then we're reaching situation in which the error is becoming closing to floating point precision. And we're gonna check how many points are required for each of the methods to compute, reach the accuracy that we desire. So we're gonna try this out in a moment. However, I think it's a relatively good time to make a break. So we're gonna have, first off, is there any question so far? Yes. Is the full set? Yes. Yeah, yeah. It's just that we thought it was better to have a single file with all the slides of this chapter, rather than having 10 PDFs, essentially. But tell us, also, give us feedback if you prefer to have individual classes, let's say, separated. We can definitely do that. It's no real problem. But yeah, it was a full deck of slides after also this class. Right. If there are no more questions for now, then we can take a break up to 11:05, and then we start again with this test. All right. We think we can start back again. Maybe you might need a bit of... Right. I hope you can see the screen. So, as we mentioned, now we're gonna give it a quick try to, let's say, see how it is going. And essentially, the way we're coding this is relatively straightforward. We have a function that is just returning us the value of the free variable in this estimation, and we want to start from our position x0 and y1 and go to 2. And in this case, we are just setting the number of steps that we want to perform, and we are going to cycle through this value and performing the evaluation. And finally, for each evaluation, we're going to get, let's say, the result. So the y value, the estimate that we get in position 2, yes? Probably not, but it's literally 5 lines of code. And so this is part of, you know, the exercise that you want to work on and make sure you're able to implement this. So most likely no, but it's literally 20 lines of code, and I'm not saying that you can do it, but it's very easy to jot down the information right now. Now, and then we're gonna get the reference value plus the error that is available there. So now our idea is that we don't know exactly how many steps we need to perform in order to achieve a certain accuracy. So we just gonna proceed in a very naive way, and essentially we are just trying to repeat this operation until our error is bigger than the value that we expect. Once we go lower, we're gonna stop and we're gonna see how many steps we need. So this should be compiled anyway. It's complicated to do this. So okay, we started, and as you can see, our error right now it's in the order of 10 to the minus 4, and it's steadily decreasing. But in order to step with accuracy 10 to the minus 6 from 1 to 2, where at the moment we are in the order of 70,000 steps. Yes. Yes. Yeah. It's the absolute error and the number of steps that we are performing to achieve that corresponding error. And of course, there were better ways of doing this. For instance, doubling up every time. But that's just to show you, and giving me also time to talk about it, that show you that the number of steps that we need to perform, the other steps that we need to perform in order to achieve a solution that is accurate to the extent that we wish, is actually not trivial, and that's fairly high, even for an interval that is only from 1 to 2, so it's like relatively small. And now, even if we are in the order of 150,000 steps, we are still not able to achieve the results that we are looking at. So we just let this cook there, and what we're gonna look now is instead, probably you're thinking like, is probably not gonna do this for all the methods. Instead, I am. But why? Because now we're gonna see in a moment that if we now turn to a second order methods, we can see that the difference is gonna be quite significant. In fact, here in only 3,000 steps, we are able to achieve an accuracy that is below 10 to the minus 6. So now you can see how the the variation between the usage of the first order method and the second order methods already provides a significant increase in performance, and a significant reduction of the number of steps that we need to perform in order to achieve the same accuracy. Now, let's see if this one is over. No, not still, but we are now approaching, because like it's adding towards 10 to the minus 5. We are almost in the order of 2000, so things are going well. In the meantime, we can also have a look at what happens when we use another second order integration, which is the midpoint. And also in this case, well, as you can see, we are obtaining essentially the same number of steps. And this is because these two methods, even though over time, if we look at it, are providing different solutions, because the approximation of the derivative of the step is different in the two methods, although the error that they are providing is the same, is of the same order. So in practice, in this case, this is gonna give us essentially the same number of steps, because that's the order and that's the magnitude that we are able to achieve by using a certain step size. So one good thing of this way of estimating the error is that independently from the methods that you are using, then the accuracy, let's say, the number of steps that you need to take with either method is going to be essentially the same in all of these cases. Right, so what happened to Euler? Nah, still there. But we're now close. Like this error is going down, and you might notice that it's going down linearly. And so the last thing that I'm gonna have a look now is the RK4 integrators, and you can see here we are taking our K1, K2, K3 steps at the right position, and then we are averaging their value in the last step as per the algorithm that we saw before. So in this case, we can try to run this one as well. And we can see that in this case, even the number is even smaller. And we can see that if we take a look at how it was 3,000 steps for second order methods, and it's 38 steps for fourth order methods. In this case, we have essentially a factor of 10, no, factor of 100, between the number of iterations that we need to step. So essentially by every order, we are getting a reduction in the number of steps that is equal to 10 to the power of the increase in the number of order. And we may test these approximation in a moment. Remember though that these evaluation come at 4 times the cost of the evaluation of a single step in the Euler case. So of course in this example, in this case, the computation is trivial and it's sufficiently fast for us not to notice. But of course, whenever you are performing much more complicated calculation over, I don't know, a system of springs that contains 100 points, 200 points, then you can definitely appreciate the difference between the, let's say, stepping in the different situations. So let's see if Euler is over. No, not really. Let's see. By the end of this class, probably we're gonna have a solution. But based on what we have seen before, we can have a rough estimation. So if second order gives us these, essentially it's probably let's say about another order of magnitude. No, like we're gonna have soon a convergence here. The number is getting smaller and smaller, but over, let's say, we're gonna get a solution in about 500,000 iteration essentially. Now I just spoiled this to you because we cannot really look at this forever, but in practice this gives you an idea of how the number of iterations that we need to perform is actually let's say very important to keep in mind, and the size of the step is particularly important. So 1 second. All right. So this is one way to sum up the results that we've seen, and it is important to also consider the fact that now essentially what we have been doing was like reducing the size of the step, but most of the time we set a certain size step and then we see how the solution looks afterwards. So here in this plot you can see how the solution differ depending on the size of the step. So now by looking at this plot you can see that whenever we are using an let's say a high order method, we're gonna achieve a better solution that is, since the error is let's say proportional in a polynomial sense to the size of the step, then our accuracy at a given after a certain period is gonna be proportional to that step. So if I reduce the step size by 2, then I'm achieving a factor of 4 in terms of accuracy when I'm using a second order method, and a factor of 2, 4, 8, 16 in a fourth order method. So to obtain a similar accuracy benefit, then the number of steps that I need to perform, for instance with Euler, is going to increase at a much faster rate than the one that I need to use for a higher order method. So here is the key difference and the key important factor whenever we are looking at two different methods, because one is going to give us the possibility to make much larger step at the similar accuracy. Yes? So it's so the question was how we factor in numerical stability in the computation. So we are now discussing all let's say explicit methods, which are the one that might have problems in terms of stability, and we're gonna have a look at these also in a couple of slides. But in general, the idea is that once you decrease, typically these methods are typically conditionally stable, which means that suppose if a certain condition is met, then the method is converging, otherwise it's not converging. So in general, if the conditional is stable, it means that this is a threshold that is gives you an upper limit on the size of the step that you can take. So you cannot make the steps larger and converge, but you can always make the steps smaller and it will converge faster. So it's more about like how large you can go rather than how small you can go. Because if you go small, it's gonna always converge in general for stable methods. Of course, if a method is unstable, it's useless by definition. And so in that sense, it's not even worth coding it. Or, well, you can code it for educational purposes, but that's as good as it gets. So this here, in this plot, is like a visual representation of what we were discussing. So you can see that if I have a step of h equal 1, and I perform a second order evaluation here, second order evaluation here, and the first order here, even if and then my accuracy essentially goes around here, if I'm using a factor of 4 smaller step using Euler, I'm still not matching on, even though I'm making 4 times the number of steps. So in general, it is, if we have the computational power to perform a certain use a certain method, then it's typically better to perform an integration using a high order method rather than using a first order one with the much smaller steps. That said, as you can see, like a second, depending on your application, a second order method, we're gonna give you an extremely good accuracy in a number of different situations. So unless you really require the accuracy to be extremely high, then it could be enough to have a second order integration method rather than a first one, but not necessarily going to a fourth order one. Right. So now, why things are inaccurate is something that we have mentioned at the beginning, and essentially is the fact that we are here rewriting again our Taylor expansion, and as you can see, what we have here is that this equation is exact if we gather all the contribution from the upper higher order terms in these let's say error term. And here you can see that whenever we are performing an Euler step, we are neglecting whatever it's down there, which is essentially our error. And as you mentioned a moment ago, the fact that we are inaccurate, or the degree to which we are inaccurate, may also lead to instability in the way that we were, in the numerical sense that we were discussing before. One example, I don't have it here, but you have it in the slides from last time, the example where we have circles. And essentially, we have seen that, maybe I still have it here somewhere as soon as I find my, right. So in this example, for those who were not there, the trajectory, the correct trajectory, is to move along the circle. But since we are discretizing our steps, our solution will inevitably move farther and farther away from the circle that we are considering. And here, as you can see, the bigger is the step, the worse is the approximation, and the faster our solution is diverging from the true solution. So, and this is, or that was one example. Another example of these was also the fact that we can have a large oscillation of the values that lead to an explosion of the value rather than converging to, let's say, the expected value and following the trajectory as we would expect. So these, the inaccuracy in the integration is not something harmless, is not something that you can just not care about, but it's something that can lead you to completely wrong solution, essentially. So one example, visual example, is something that similar to what I was drawing before. So if we are stepping and using a first order method, here you can see that we always have access not to the black line, is that blue line, but only to the points that providing our estimation. And once we arrive here, our estimation of the derivative is completely off with respect to the actual trajectory of our function. Of course, these can be, one could say, oh, but you just need to take smaller step. And you would be right. In fact, this error here, as you can see, is proportional to the size of h. So the smaller is h, the smaller is the error. And it's something that we have seen also in the calculation before when we were running Euler, because the more we were increasing the number of steps on a given length, before we were trying to discretize a domain that has length 1, and we were using n steps to do this. So our value of h was just 1/n. It means that the higher is the number of points that we are considering, in the given interval, the smaller is the step size that we are considering. So in that sense, the error is gonna be proportional to some extent to the size of the step. But again, as we have seen before, and we can write actually a bound, at least in this case for Euler. In fact, the error is gonna be bounded between 0, if we are very lucky, or the first term that we have removed from the expansion, because in general, higher terms, if you remember, the terms were in the form of yi divided by the factorial I times let's say h to the power of I. So of course, these two terms become very one large and very the factorial of I becomes very large very fast. The power of h to I is gonna become, since h is usually very small, then it's gonna become small because it's smaller than 1 typically, so it's gonna go down as well. So all the terms in this expansion that are higher than order 5, 6, and so on and so forth typically have very small value comparatively to the other terms. So and the higher is the value of I, the smaller is the contribution that these terms are providing, which means that in general we are always able to bound the error, to write a bound for the error based on the on the smallest derivative that we are neglecting in this expansion. So in this specific case is the second order one here. Now, again, the takeaway message here is the more step you make, the lower is the error. But of course, you're gonna go slower in time, and typically you're not interested in you're interested in long time behavior and see what is happening after a certain time step, and you cannot just perform 10,000 steps, as you can see, and just see the solution after a very short time step. So this is something actually we brought out before through the question and through the example that we made. So the error that we are with a given fixed number of steps, if we're using a certain number of steps, for a first order method is gonna provide an error that is much higher than an nth order method. And even though, of course, one should consider that higher order methods, again, as I said it probably 10 times in this class, but it's something that needs to be, it's essentially the main point here in the discussion. It's like the higher is the order, the higher is the number of the computational power that you need to put for a single step. And we have diminishing, as we saw in the table before, we have diminishing returns as soon as the order increases beyond the fourth one. So, yeah. Provided that we stay in the limits of numerical stability, and in general, let's say, there are a few methods that are not numerically stable, so you need to provide, as we were mentioning before, a step size that is lower than a certain amount in order for the integration to converge to sensible value and not to diverge in that way that we saw. We can usually use higher order accuracy to perform less step and cover the same amount of time, because in the end that's our goal. And in general, we have an expression that we can use to bound the error of the n derivative in a given interval, and that's given from this expression. As you can see, like n plays a role, an important role, a polynomial role in this context, in the way the error can be limited in these cases. So now, this is what we do in theory, and that's what the theory of numerical integration tells us. But in practice, now, what we are trying to achieve here, our goal, so to speak, is to have an integration and a simulation that makes sense, and the level of the quality of the simulation depends on our goal. So if we are trying to make a physical simulation, of course we need to have a very accurate method and a very accurate integration of the system, because our interest is to see what is happening in a physical level, extract physical knowledge, and we cannot just make up the results. On the other hand, if we are trying to simulate a game, these boundaries are a little bit more relaxed. Let's say, let's assume we are trying to design the movement of a ball in a football game. On one end, there is a correct, in principle, there is a correct trajectory, which ends in the goal. However, our numerical integration might gives us something that looks like this. So now you can see that these two solutions are not very far apart, but for the way football is designed, the fact that we are within or without a certain area, which is the area of the goal net, will give us for the game a completely different result. And these would not be, let's say, acceptable if you were really wanted to match the physics, but in practice for a game is completely fine, and it is a completely reasonable behavior, because then let's say, it's not, let's say, its visual validity is sufficient for our game to look legitimate. Then if it is exactly within or slightly out of the goal, then this will rule the game in a different way. But in general, it's still plausible. What we cannot afford is something that looks like this, because in that case our trajectory is completely far from what we expect from it, what reality is, and that is gonna essentially turn out to be very weird, essentially, and non playable experience in a sense. So again, we are the leading team here is accuracy versus computational cost. So make sure that you do things in a way that is accurate enough for things to look sensible, but of course keep in mind that this more accuracy comes always at the cost of a higher computational cost. So this was essentially one way of doing the computation, and the most widespread one in practice. Although there are other alternatives, and one of them is trying to use what they are the so-called state-based method. So in this case, instead, and something that I mentioned before, so instead of trying to achieve higher accuracy by trying to provide a better evaluation of the derivatives, what we are trying to do is to perform this by using the states that we have already computed before. So if we have 2 points and we are able to provide possibly a better estimation of the function by storing those information. So let's consider, for instance, a second order ODE, which is what you would get, for instance, if you are trying to compute the acceleration of something. And one approach to compute the velocity, for instance, is to use what is called a velocity verolet. So in this approach, we have, let's say, we know what is the expansion on the regular expansion on the first line, and then we have that the second one is the velocity verolet. And in this case, as you can see, even though this expression is slightly different, and we are computing the first derivative of let's say the approximation of the first order derivative, then we are getting through this method the same level of accuracy of the of an expansion to the second order method. And of course we need to first calculate this term, and this is usually done computing first the let's say the position, let's say in the value of yn plus 1, and we can derive it or obtain a derivation an estimation, sorry, of the second order derivative in that point. And by using that information and the stored data for the derivative in the previous point, then we can calculate with higher accuracy the first order derivative. Now it is important to notice that now that we are moving our trade-off from computation to memory. So now in order to achieve the same accuracy, we don't necessarily need to do more calculation, but we are need to store the value of a certain function, of a certain acceleration, and so on and so forth, in different steps. Now this of course seems trivial for a single point, but at the moment you have 1,000 springs and 1,000 points in your domain, your object that you're discretizing, then you need to multiply. You need to have an acceleration information for each and every point, which is effectively, let's say, doubling or tripling or quadrupling the memory requirement for your integration scheme to work. So it's always, again, trade-offs between what you want to get and what you can achieve with the power that you have. The other alternative to this is actually perform what is implicit integration. And as we mentioned before, our scheme, let's take Euler because it's relatively easy to write, is something that looks like this. In this expression, the important part is that on the right side of the equation, we only have values that are computed at the nth step. So in principle, we all know those values exactly because we have already computed them. Now, when we are, these approaches are called explicit. What we can do is that we can write an implicit method. So in this case, instead of using the approximation of the derivative at point xn, what we are doing is that we are using the approximation at the step n plus 1, which is slightly different, but this difference is quite important for the reason that now on the right side of the equation we have the value of yn plus 1, which in principle we don't know. So, and this is a problem because of course this is not we cannot really solve directly this expression, because in order to compute the value of f, we need to know the value of yn plus 1. So in practice, what we do is that we need to arrange and collect all the coefficients that depend on n plus 1, on yn plus 1, and write essentially the same equation in a matrix form like this, so that all the terms containing yn plus 1 are on the left side, and the rest contains only terms that are known with respect to yn and xn plus 1. And xn plus 1 is not particularly important for us because we know it exactly. It's just xn plus h because it's fairly trivial. So that's not a problem. But yn plus 1 is actually, let's say, problematic in order to perform the computation. So, and the next step is what we get here. What we get here is essentially a linear system that is a function that needs to be solved in order to obtain yn plus 1. And so what we just need to do is just that we need to invert these A matrix in order to obtain our value of yn plus 1. In the case, let's say, let's dig up our example that we were using before. So we have y prime equal to y, and that's relatively, since it's one-dimensional, we can actually see that in practice. So if we are writing our implicit scheme here, what we get is something that looks like this. So this is f of x n plus 1, yn plus 1, which becomes yn plus h times yn plus 1, right? So as you can see, we have yn plus 1 on both sides, and we can easily gather the two terms on one side. So in this specific situation, and it's a scalar equation, so it's much easier and it's trivial to invert. This part will play the role of our matrix A, and this is gonna be our vector B. And of course, in this case, finding the solution is relatively trivial, because we just need to divide by 1 minus h, and that's as easy as it gets. But in general, this is not necessarily easy. So, for instance, we might need to perform an implicit integration of a system that looks like this. Now, the matrix that we get from here is encodes the entire connectivity of the system. So the only, let's say, connection that we're gonna see between the different springs is gonna be given by the fact that the different points are connected. So if we can try to give a visual representation of how the matrix looks like, so something like this. So of course, every point in our diagonal is gonna be equal to the identity, because it's how the point is interacting with itself. So like just stays the same if there are no other forces. But in the off diagonal, let's say, terms, we can actually see and find the different correlation, different relationship between the different points. What is interesting here is the fact that now all the 3 points in our system are connected. So the matrix A in this case is full. So all the terms are full. If in our system there are some points that are not directly connected by springs, then in that case what we have is that some of the interaction, let's say we don't have a spring between B and C, what happens is that this interaction will not exist, because there is no force that relates the movement of B and C. So in a sense, the matrix A, as is written there, encodes the connectivity of the system, and that can help you out. On top of that, I'll come to your question in a second, we are also removing the interaction between, not only the interaction of C on B, but also the interaction of B on C. Because if a system is only made of springs, then all the interactions are, let's say, opposite and opposed, essentially. So neither one will influence the former and vice versa, essentially. Yes? Yes. I mean, actually, you know, this non-existing means 0. Yes, it means 0 because what is happening there is, let's say, this is an interpretation, but this matrix A comes from the way you are constructing the forces. So let's say this structure can, the fact that you can see this structure um, emerges directly from the, if you are constructed correctly the system, this will match essentially. So it's more like a sanity check, that if there is an interaction that should be there is there, and if there is not an interaction that should not be there, it's also not there. Essentially, like things that should be there are there, and things that are not are not. Of course, otherwise that becomes there is probably an error in the code. That's the usual take-home message. And so the question, of course, is why would one well, that maybe we look at it later, but why we're gonna do this, that's a point that for a moment. But so what is important here is that typically we are trying to use these approaches for linear systems, and the encoding of the dependencies in the state variables is easily seen when the matrix is linear. We can also have nonlinear dependencies, but of course these might become more complicated, especially if the dependencies are in yn+1, because in that case then we have matricial equation that we need to solve rather than just a linear solve, and that's of course much more involved and much more complicated, so typically not recommended for these cases. So let's have a quick look at the difference between the use of an implicit method and of an explicit one. So this is what our explicit Euler solver would do, and that's relatively straightforward. It's something that we have seen already before. What graphically, what an implicit method is doing is that it's using the information of the derivative at the next step, at least our approximation of it, in order to obtain our estimate. Now, as always, we don't know this quantity. What we really know is just the derivative as it is computed here. And of course, again, it's difficult to see more in a graphical way here, because we don't know this point, we don't know the derivative there until we know the value of that point, because f of x n plus 1 yn plus 1 depends on yn plus 1. But through the solution of the linear system, then we get to see what is the actual solution. One visual, let's say, feature that we can see is that where typically Euler tends to overshoot the solution, then explicit Euler tends to overshoot, while implicit Euler tends to instead undershoot. So if you look at the curvature here, what you see is that the Euler tends to go, let's say, out, while implicit tends to go in. So in the example that we had before, for instance, where we had all the different circles, what is going to happen is that if we are using what is orange, let's take red, explicit Euler, what is happening is that we are diverging in this direction, whereas if we are using implicit Euler, what is happening is that instead we're gonna converge to 0, essentially. Neither behavior is correct, but there are properties that can, let's say, the fact that the solution is not diverging to infinity, but rather kind of converging to something very small, can be a pro in our, let's say, can be used to our advantage in the integration. All right, I think is a good moment to make a small break, but first let's answer this question. Yeah, no, no, I see what you mean. So essentially, the question was just for people not in the room, whether implicit tolerance is used in practice. Now, we're gonna see in a moment that uh, implicit integration has some perks that we can use, despite the fact that it has a relatively large computational cost, because typically inverting, of course, if you imagine a system of springs, you cannot solve for each and every point individually, but your solution will entail solving for all the points at the same time, which means that in practice, in order to do one single estimate, you're gonna solve a n by n matrix inversion. That, of course, again, for a small system is not problematic, but if you're considering hundreds or thousands of points, then it starts to be computationally intensive. I would not, but there are interesting properties that we're gonna see after the break that makes them a possible and interesting solution for certain use cases. In general, I wouldn't use them in tandem with other methods, because you would need to do a lean solve to get an estimate and then correct it with an explicit step, because then OIN in practice is providing an implicit step unless you're performing 2 times an implicit one, and which is like twice the lean cost solve. But in that case, we are mixing implicit and explicit, and we will see that, I mean, there are use cases also for that, but in general, is not may not be recommended, let's say. All right, I think we can have a break until 12ish, and then we start again. right. So we stopped here at the implicit Euler step and see how was behaving. Now, essentially, why would one use this in games? So the answer is that is related to what you were discussing before, which is essentially the stability of this system. So fully, which is maybe the keyword here, like fully implicit schemes are unconditionally stable, which means that whatever the size of the step that I'm taking, then I'm still getting the same stability, which means that my solution will not diverge to infinity, which is already a good starting point. Well, it will diverge to infinity if the actual solution will diverge to infinity, but at least our error will not. Well, depends. If it's diverging to infinity and we are infinitely close, they are still at infinity. So but again, in practice, though, there are some caveats and small things that we need to keep in mind. So, and this was discussed a moment ago in the break, that as soon as you have a more complex system, then the size of the matrices that we need to invert becomes uncomfortably large. And of course, especially you will see what happens when we are considering a lot of mass spring system of mass springs in an individual system, and a lot of our ability to do this integration and do it fast and accurately will depend on on how we will solve this linear system. Because of course, if you have a certain specific structure, which is, for instance, in this case, we know that our system is, if we have only a mass spring system, for instance, our matrix is gonna be symmetric, because despite the fact that interaction can or cannot be there, they are mutual between the individual element of the mass spring systems, which means, of course, then if an element is present for the interaction between B and C, there will be also the interaction between C and B, independently of the fact that there is or not this interaction. So either it's 0 or it is a value, but it's gonna be always present in both cases. So we have a symmetric system, and these can be solved with more efficient methods than what is usually do for an arbitrary matrix that we can do. So nonlinear systems are much more difficult to manage, and usually those, in order to manage nonlinear system, we typically resort to different approaches that are tailored to the application. Say, for instance, we want to model fluids. We have nonlinear interaction caused by advection of the fluids, and typically there is a little bit of, let's say, work that needs to be done in order to perform the most efficient integration in those cases. Now, one thing for games is that, as we said, these trajectories from the implicit integration scheme will result in an undershooting of the value, to the sense that it's essentially acting as a sort of damping in the solution that might lead to dynamics that are not fully representative, or they can be, well, in a qualitative sense, boring. So like things will not behave as we necessarily expect to, because they are just always going kind of slower or not as far as we expect, just because we are using this kind of integration methods. And one point that it's important to make here is that one can integrate, mix and match integration systems. So one can integrate partially as an explicit methods and partially as an implicit methods. Although in this context, if we are mixing the two, then we are losing most of the benefits that we get from using implicit integration. So, for instance, if we are using, as we were mentioning before, the implicit Euler to do the, let's say, alpha step in a midpoint method, in a Hoyne method, then the resulting scheme will still be limited by the numerical stability constraint that we have in these explicit methods, and we will benefit less from this implicit integration. One case in which this is interesting, for instance, is fluids. Again, we like fluids, because there is a nonlinear part, and this nonlinear part, if typically provides very strict, let's say, conditions on the step size in order to maintain the stability of the computation, the numerical stability of the computation. So sometimes it's one part of the equation is integrated implicitly, just because then we still have a condition on the stability, but it's gonna be only related to the linear part of this equation, skipping the most constraining part, which is then, let's say, treated using an implicit scheme. So in general, although the important part is that in games they don't really find that much application, because even though they're unconditionally stable, they may look boring in first place, which is a biggest no for games. And on the other end, they can be extremely computationally expensive in this case. But for instance, if we want to make a simulation of something, a transient, so let's say we have I don't know, a boat that is starting moving, and we are not interested in the initial transient. We want to step through the initial transient as fast as we can, and we want to see how this boat is moving in cruise mode, let's say, in the moment after the initial transient is gone. And then in this sense, an implicit methods can be helpful, because we can integrate with somewhat arbitrarily large time steps at the beginning, and just neglect the behavior there, or pass through the behavior there in a faster way, and then we don't need to care too much about the stability of the integration, because we know that it's going to be stable in any case. So, a bit of a summary. Usually we are not able to perform an analytic integration of the equation of motion that we are interested in. So the only thing that we can really do is to approximate the solution with a numerical scheme. The numerical scheme, the numerical scheme gives us a certain accuracy that we can choose depending on the, let's say, on the requirements of our solution, and usually the next solution is based on the current state that we have, which is something that we can obtain in an autoregressive way from previous solution and stepping over time. So given an initial state, we step forward in time and typically display the results. These will lead us to an interaction with the player of the game that we then provide a reaction or an action or a forcing in, after all, that gonna be needed to be kept into account whenever we are computing the reaction to the user input. So the Euler step is the most basic but also the least accurate approach that we can have for this integration. We can definitely use higher order methods. You are actually, I would say, advised and recommended to use higher order system, because we have much higher accuracy with good trade-off with respect to computational cost. And in any case, remember that it's always the largest error that you make that is gonna influence your system. So let's say you always need to keep into account, it's always the weakest link of the chain that will make your simulation blow up. So one always need to tune a little bit the elements and of the different parameters in the integrators, including orders and step size, in order to see, to check, and to obtain a solution that works and provides a reasonable results. Implicit methods are unconditionally stable, which is very nice, but typically they are not that much used because they require much more complicated solution procedure. Yeah, know what now. Usually, you can be kind of oblivious of all this if you're playing a game, but now in the moment you want to code a game, then you really need to make sure that you know what is going on, because by knowing this, you know also what to expect from your simulator. So if you're using a physics engine, for instance, and you know they are performing implicit integration, you know what are the pros and cons of this approach, and if you see too much dumping there, then maybe you need to change the integrator in order to make the dynamics more plausible or more pleasurable to some extent. So now, what happens if we try to use all that we learned in the math in mass spring systems? So now I know it's a little bit complicated, but we have yet again a return of the previous notation. So now what I'm referring to are the position. What x will refer to the position of the individual mass points, and it's gonna be typically a vector because we have more than one point. And also we have a vector containing the velocity of each individual point, the acceleration of each individual point, and m is gonna indicate mass of those. The only thing that I'm gonna mention here is just that with the subscript I, we are indicating essentially which of the various points in our system we are indicating. Typically, we just number them one after the other. So it's this is a friend that we have seen a long time ago. Now we can see it with different eyes because we have been looking at ODEs for quite some time at this point, and we can definitely see that this is an ODE. There is only one variable, so it's not a PDE, and we know that we can rewrite this system that is a second order derivative system as a first order one using by the change of variables that we have seen in the previous class. And what we do in practice is that we perform an integration based on these rules, based on the fact that the derivative or the differential relationship that we see here, so that the velocity is the first derivative of the position, and the acceleration can be obtained through Newton's formula. So what happens at each time step is that, as we have seen also last time, what we do is that we compute all the elastic forces, considering that these are the only forces that are acting in our system, and then for each and every point we can perform the integration of position and of the velocity. Now, one question that was asked last time was, does it matter, or what is the correct order of the integration? Should I integrate first the position and then the velocity, or vice versa, and so on and so forth? If we are using the Euler step and explicit Euler step, these really doesn't change, because we have seen that in this case we are not using information from the new step, which is the information that we are obtaining from these equations. So these will lead us to x n plus 1, and these will lead us to v n plus 1. But we don't need either to compute neither of the previous ones. So which means that we can perform these in any order, and this is going to give us anyway the correct solution. On the other end, which is what I wanted to say here. So there is no reuse of the new data, and which means that it's not important the order in which we are performing the operations. One thing to keep in mind though is that you want to make sure that you're not rewriting variables that you need to use in these operations. So keep in mind where if you only have allocated the space for the position of the springs and you rewrite constantly in the same space, these can work, but you need to make sure that you're not using up-to-date information to perform a step that would not need those information. If we are doing midpoint integration instead, we need to integrate both position and velocity with this approach. And since we have our values at the given time step, and we need to perform these integration here, and in order to compute, let's say, intermediate points, we cannot just overwrite the variables that we were mentioning before and as we were doing. So now these are the steps that we would need to perform for the position. So as you can see, the first step is again our predictor step, and in which we have half a step. We use the velocity at this time that we have already at this time, and then we obtain an estimation of the position. However, when we are performing the full step, we need information from the midpoint in the, let's say we call it the corrector. And this is very important to notice that we don't have this piece of information v tilde at this point. So what we need to do is that we need to consider the velocities, and the velocities have this form, and here from this prediction of the velocity, this prediction of the velocity needs to be used in order to compute the position. So now the two steps are not separate anymore, but we need to consider them in tandem, and because we need to use one and the other, and also vice versa. When we are computing the acceleration for the velocity steps, we need x tilde. So at this point we have interdependency that we need to consider. Now, if we are performing the operation, we need to perform it then in this order. So first off, we do the prediction step for both position and velocity, and then we perform, which are these step here 1 and 2, let's say, and then we perform the steps for the correction for both the velocity and speed. One could notice that if we are performing this, the operation in this order, what happens is that we can perform either first 1 and then 2, or vice versa, and it doesn't change anything because there is no interdependency within the predictor step, but there is an interdependency from predictor to the corrector. So what we do is that we take v and x, we compute and store the solution at time t plus h and a half for the position there, and we can compute also the same for v, so the two predictor step, and then based on this information we can compute the position on the second step, and as well using the temporary position and temporary velocity, which here represent x tilde and v tilde, we can compute the velocity at the step farther down. Now this is more convoluted than the Euler step that we have seen before, and of course it does get worse as soon as we try to do this in using Runge-Kutta. So the procedure is very similar to the one that we used in the midpoint method. However, we always need to make sure that we compute, we need to kind of interleave the value, the computation of x and v, and so there will be a k1, 2, 3, and 4 for the position, and k1, 2, 3, and 4 for the velocity, and we need to step by each and every k one at a time, and only get that, then we can have the final weighted value for that situation. A method like this, of course, needs more storage. So what we need to do is that we need to have 8 vectors, so which corresponds to the k-value essentially, so to the temporary velocity and position that we are computing in each and every step, in order to compute the final weighted average. Another yet different approach to do this computation is to use a leapfrog integrator, and this is somewhat special because it helps with the fact that we only have to do one force evaluation, even so we gonna get a second order accuracy. Also in this case, we need to have an interleaved update of velocity and position, and this, let's say the gist of this integration method is written here. And the nice thing is that actually the implementation is relatively trivial, and despite that, so we have less vector to keep track of in our integration steps. However, even though it's extremely simple, we can definitely obtain higher accuracy and the same accuracy as actually midpoint and OIN methods for these approach. So yes, this is essentially the way our Euler methods look like after we compute the let's say the forces, we just get the velocities. In the leapfrog, you can see in the previous step, we first compute the velocity and then use them to compute the position. So what is happening is that we are actually computing the two variables at, let's say, somewhat different times. So if this is x and this is v, this is the stepping at every h. So this is 0, this is h, 2h, and so on and so forth. We are evaluating the velocities at the midpoints. So actually the velocities are computed in these points, and that's the reason why actually we need to use and initialize the velocity in a different time step. We can do that, for instance, doing a first half step Euler in order to obtain this velocity. But once we have initialized this, when we can perform the computation with very limited information. So what happens in this case, which is what I want to mention here. So what we do is that we compute the forces, we then integrate the velocity but using the current position, and then we proceed with the integration of the position. Now, of course, since we are, despite the fact that we have shifted the velocity, then the step of integrator is always the same. So it doesn't really change much in that sense. Yeah. Now I'm here. There are a couple of slides regarding how this is derived, but this is just for you to know that this just not comes from nowhere, but we can have an analytical way of recovering this information and this method that essentially relies on other value. So the important part for me now is to have a look at the actual discretization of our system. So walk through the entire procedure of the integration system, or how we integrate the dynamics of a system. So we start with the initial model. We have our let's say set of points and set of springs. Now the biggest issue is that it's not trivial to define a model, and let's say once we have a model, we need to work with that for all the simulation, because getting a refined model is something that is absolutely not trivial. So let's say now we did all of the computation here with this model here on the left, sorry, and we want to we increase our computational power, and we want to use a refined model, a better model with more points, so that we get a similar computation. Now, and I have, say, 9 points instead of 4. One issue is to define the spring connection in this system, so that this system is perfectly equivalent to the one that we have on the other side. So, and not only that, but also how, assuming that we know how to connect the springs, how do we choose their stiffness? Let me make an example. If I am using the same approach that we have been using before, you can see here that let's say there are many springs and many more springs, and there are springs that were not there previously. So, for instance, this one could be very hard to, reproduce in the different system, considering that there was no points and was no spring in that point. But even more critical is the definition of these two springs. So, for instance, first off, well, there are formulas that gives us the value of springs that are in series or in parallel. So if you have two springs like this, K1 and K2, then you can compute the equivalent stiffness of the spring. Or if you have two springs in series, you can tell what is the equivalent spring resistance. However, in this case, these points are not connected only by those two springs, but there is an entire set of system, and there is no trivial way to do this. But more importantly, let's consider point 1 and 2. Now, these 2 points are connected by a spring, which means that if they get closer or farther away, then they will experience a force. However, if now I take point 1 and point 2 and I fold these 2 points one on top of the other, since these 2 points are not connected directly by a spring, essentially this deformation will not make the body experience any force. Of course, it's difficult to visualize because it's not a physical behavior, but that's really the biggest issue here. So by refining the model, we are introducing a folding behavior that doesn't make any sense. So now we would need to fix this by using a different approach, because if these 2 points collapse on top of each other, on top of the other, there is nothing in our system that would prevent that, in principle. And there will be no repulsive forces between these 2 points, because there are no interaction in the matrix, in the connection matrix that we are building at this point. So that's something that we really need to keep in mind whenever we are dealing with these systems. So even designing the original, let's say, mass spring system is not trivial, and some thought needs to be put in this direction. So I just want to close the lecture with some example / case study that could be interesting to show that all these is just not for torture you, but just because you can actually use those things to build games. And one interesting example is from the game program at CMU in 2005, and so essentially the goal was to create, with the project of the course, was to create a game, and they had 7 days to do that, and a team, single person, and you needed to come up with something in order to pass the course. And one example that it's something that maybe you've seen, maybe you've not, is this game that is called the World of Goo, which essentially relies heavily on mass spring systems, and the goal is to reach a certain height or a certain point in the map. This was, let's say, distributed as a game, as a free-to-play game, and was actually took up by the community to the point that a company actually redesigned the game and essentially listened to the fan base to develop the game in a way that was interesting enough, and let's say that's represent a sort of success story that we have from there. And I will just show you in a moment the gameplay of this game, if I find it. And you will see that there is something extremely familiar here, because the goal of the game is essentially, we don't need audio to be fair, but it's there anyway, is essentially the goal is to reach the top of the pipe, and these structure that you see here are awfully familiar to mass spring systems, and so essentially this game is just relies on this mass spring system to build a gameplay and build an experience that can be played and can be appreciated by players. So let's see, there are, one could see that this was, well, relatively trivial, but as soon as we go to more complicated levels, you can see, for instance, now we need to close the gap, and of course there is gravity that is playing against, and if you were not using a reinforcement here, then you would not be able, your bridge would crash, and still all these is just, again, a mass spring system and nothing more. So that's something that can be an interesting point to say that all these does not is something that you can definitely find use and can definitely be applied to a game to make it actually an interesting experience. And let's see if this gameplay fails at least once. Yeah, so you can see that, let's say, gravity will drag you down anyway at a certain point, so will make the game let's say more difficult as they go on. So but this was just to make a point regarding the fact that it's not something out of the world, and it's something that you can definitely end up using, and that you're gonna be using to some extent if you're dealing with bodies and so on and so forth. So quick wrap up of our mass spring system that is now coming to an end. Next week we're gonna have a different topic. So from the numerical integration side, we have that, to remember that we have different methods. They can be explicit, implicit, so on and so forth, but you need to have it an idea at least of what are the limitations and possibilities of the different methods. For mass spring system, in general, there is not much use for explicit Euler because of all the drawbacks that we have seen, except the fact that it's easy to code, but it's all about it. It's just about it, and it's not so much more than that. One can use leapfrog for the for what we have seen before, and whenever we are using this kind of system, we need to try to prevent spring inversions, which is what I was describing in when we were talking about the discretization. So essentially, structure that fold onto themselves just because we have discretized them poorly, essentially. And essentially, numerical integration, now we have seen it for mass spring system, but we try to show you and present you the results in a way that makes you aware of the fact that this is used beyond, it's used in math in general, and its uses beyond the just getting mass spring system. You can use it for integrating equation of any sort, and that's for these. They are essentially anywhere, and anytime you want to do a physical simulation, willing or not, you're gonna need to deal with the time and time integration. Regarding implementation, normally one could think that it's much more fun to start with a complex example, and it's usually fun only in the short term. So in general it is not, because it's very difficult to verify what you're doing, and oftentimes, sorry, I just talk just with the delay of the slides. It's very it's only short time fun. It's very difficult to verify what you're doing. If anything breaks, you have no idea what broke, and it's always difficult to debug those codes if you're trying to use it on a system that is relatively large. So it's actually much better to start with a very simple example, making sure that it works, and only then scale up and see the results on larger system. Of course, like looking a single spring or 3 springs connected in a triangle is not particularly fun at the beginning, but if we want to make sure that things will work also when we're using tens or hundreds of springs, it's much better to start small and build up from there. Of course, you should do things that are simple but not unnecessarily simple, because otherwise it's not give you enough insight. So, final slides for today is what you should know by now, or at least once you go back to this content and study this, is how to construct and parameterize a mass spring system and compute the dynamics according the numerical integration system that we have described before. We are able, in principle, if willing to calculate by hand the solution of very simple spring networks, as it was seen mostly in the tutorial session, in the works session, and know what are the limitations of the model that we are considering, and also based on the discretization depending on the integration system that we are considering. On top of that, we know the different integration methods and which one we would like to use depending on the different requirements that we have. And with this, I am actually done for today. The question is if there is, well, my question is to you is if there is any question for you or by you for me before we end this class. No? In any case, of course, you can reach to us via email, via Zulip, via whatever. If you have any question that comes up later on, the slides are uploaded on Moodle, and yeah, please reach us if you have any other question. Thank you.